Hello, everyone, and welcome to Chapter 7, Part 2 lecture video. So let me head on over to the PowerPoint slide. All right, today we are going to be continuing to talk about SN2 reactions and now talking about the kinetics of the reaction. So what we see is certain substrates have different reactivity towards SN2 reactions. You can see that these are described as a tertiary alkyl halide, secondary, primary, and also methyl. And the reactivity moves from tertiary, which are actually unreactive in SN2 reactions, all the way towards the methyl alkyl halides, which are the most reactive in an SN2 reaction. Let's look at some different substrates where they've actually measured the kinetics to be able to figure this out. What we see are some relative rates for different substituents in an SN2 reaction. The substrate was treated with probably sodium iodide in acetone, which we'll find out is a great solvent for SN2 reactions in a little bit at room temperature. And then they measure the formation of the products. And recall that SN2 reactions are one-step reactions, so that one step is the rate determining step. So the structure here on the left-hand column looks at branching at the alpha carbon. Recall that the alpha carbon is the carbon attached to the halogen. And if it's just a methyl group, we call it methyl. If the alpha carbon has one carbon attached, we call that a primary alkyl halide. This would be a secondary followed by a tertiary alkyl halide. We see that the relative rate goes down to essentially negligible or no reaction with a tertiary alkyl halide, which shows us that branching at the alpha carbon decreases its reactivity in an SN2 reaction. They also looked at the effect of substituents on the beta carbon. The beta carbon is the carbon attached to the alpha carbon. And we can see that in this case, it just has 3 hydrogens versus an additional substituent with a methyl and 2 hydrogens, 2 methyls or 3 methyls. We're looking at increased steric hindrance at the beta carbon. And they also see an effect on the relative rate in that it is diminished with additional branching or steric hindrance at the beta carbon. So this shows us that less sterically hindered both alpha and beta carbons are ideal for SN2 reactions, which explains that reactivity, relative reactivity that we saw in the last slide. The reason for this is because, as we know in an SN2 reaction, the nucleophile approaches the backside of the alpha carbon and starts to form a bond at the same time as the carbon to leaving group bond starts to break. So because the nucleophile has to approach the alpha carbon and that's involved in the rate determining step, then it makes sense that less steric hindrance will lower the activation energy or lower the transition state energy for that attack. So as we increase branching at the alpha carbon, the transition state energy increases, which increases the activation energy, which slows down the rate. So we can see here that when we're talking about the rate, we're looking at the energy of activation. And again, this is just a one-step reaction because we're looking at an SN2 reaction. So recall the nucleophile has to approach the backside of the carbon and start to form a bond as the leaving group starts to leave. So if there is less steric hindrance with the groups attached to the alpha carbon, then the transition state energy is lower. If there was more steric hindrance, the transition state energy would go higher. Right? So then the red line would have to go up much higher. So that's why we see a difference in the rate. So recall that it's activation energy that we're looking at to rationalize the rate. But if we were talking about the thermodynamics of the reaction, that would be the difference in energy between the reactants and the products. And this one is an exothermic reaction. Okay, so this is another visual to show you that as you increase substitution or steric hindrance at the alpha carbon, the transition state energy goes up because the nucleophile is going to run into this electron group and it will repel it, right? So that will raise the energy of the transition state. So we'll see that it's only, they stopped here with the secondary substrate because past that, the activation energy would be too high and the reaction has just so slow of a rate that it does not occur. So it's really important that you understand that tertiary substrates do not react in SN2 reactions, again, because the rate is too slow. The best substrates for an SN2 reaction are methyl or primary alkyl halides, and the reaction slows down considerably with secondary alkyl halides. So in some cases, it will work with a secondary alkyl halide, and in some cases, we'll get a different reaction occurring, which we'll learn about later. So because the nucleophile is involved in the rate determining step, we need a strong nucleophile for an SN2 reaction. So here are some examples. Hydroxide is considered a strong nucleophile. It has a full negative charge on an oxygen atom, compared with water, which is a weaker nucleophile because it only has a partial negative charge on its oxygen atom. So strong nucleophiles are best and not very sterically hindered substrates. So this would be a methyl alkyl iodide. We're great in these reactions. So this is a much faster reaction because not only does it have a ideal substrate that's not sterically hindered, but it also uses a strong nucleophile. We're going to be learning about what is a strong nucleophile. One thing to note is that strong nucleophiles are correlated with strong bases, which means it's measured differently because nucleophile strength is measured based on the rate of reaction for different nucleophiles in the with all other conditions being the same, whereas the strength of a base is measured in an acid-base reaction. So it's more of a thermodynamic principle versus a kinetic principle with the nucleophile. But regardless, both of these features tend to go together. So oftentimes, strong nucleophiles are also strong bases. And that's because a strong base needs to donate a pair of electrons to a proton, and a strong nucleophile needs to donate a pair of electrons to an electrophile. So they're doing a very similar job. The difference is that the proton is small, so we don't have to worry about steric hindrance. But an electrophile, there's a variety of electrophiles, right? This is methyl iodide, but there's a lot of other substrates we can use. So that also depends on some other factors as well. And so we're going to look at factors that affect nucleophile strength, such as how much charge is on the atom, right? Is there a full formal negative charge or only a partial negative charge? And other factors such as steric bulk, which can affect both the nucleophile could be bulky, and also the substrate. And then factors like resonance are important as well in terms of nucleophile strength, because if a nucleophile is resonance stabilized and compared to something else that's not resonance stabilized, that resonance stabilized nucleophile is more stable and therefore it's less reactive. So here are some commonly used nucleophiles in substitution reactions. We see them classified as strong versus weak nucleophiles. What you'll notice about the weak nucleophiles is that these are neutral, right? They're water and different alcohols. And because they don't have that full formal negative charge, they are not as strong as some other nucleophiles that do have that full formal negative charge. And so recall that it is important to use a strong nucleophile in an SN2 reaction because that nucleophile is involved in the rate determining step. And another factor that's important as well is that the solvent also affects nucleophilicity. And so that's a little bit confusing because sometimes we categorize nucleophiles a certain way based on their strength, but that's sort of dependent on the solvent that's being used. So solvents can be categorized as what we call polar protic or polar aprotic. And nucleophile strength can actually change in different solvents. So in one case, you might see that fluoride is a better nucleophile than chloride in a certain solvent. But if you change the solvent, then it could be chloride is a better nucleophile than fluoride. You can see that the solvent is going to play a large role as well. And we're going to talk about the solvent right now. So solvent effects, right? So the best solvent for an SN2 reaction is what's called a polar aprotic solvent. Aprotic means not protic, and the word protic refers to the ability of a solvent to hydrogen bond. You can see here that the hydrogen in red over here is attached to an electronegative atom, either oxygen or nitrogen. So that makes all of these protic solvents because they have OH or NH groups, which can hydrogen bond. Polar aprotic solvents are also polar, but they don't contain any hydrogens attached to oxygen or nitrogen, and therefore there's no hydrogen bonding going on in those molecules. So these solvents actually affect the reaction by their ability to either stabilize and solvate anions in the reaction. So remember that oftentimes our strong nucleophile is an anion, right? It's a negatively charged species. And in one case, the solvents really stabilize that negative charged nucleophile and make it a poorer nucleophile. And in another case, that doesn't happen, right? So the reason why polar aprotic solvents are ideal for SN2 reactions are because they stabilize cations better than anions. And because they're not stabilizing the anions, those anions are more reactive and the activation energy is lower for those reactions. We'll see what that looks like coming up on some different slides and the reason why. Okay, so let's look at how these factors play into the strength of a nucleophile in a polar protic versus polar aprotic solvent. Okay, so like I was talking about with a polar aprotic solvent, anions are not stabilized as well as cations. And the reason for that is because with a polar aprotic solvent, the outside of the molecule has a partial negative charge, and the partial positively charged part of the molecule is typically buried inside the structure. So it's less accessible to be able to coordinate and stabilize an anion. So the opposite actually happens, and we'll see that in the next class. If we used a polar protic solvent, then this anion would be stabilized. And if it's stabilized, it's lower energy, which means that it's going to have a higher activation energy to overcome to be able to react. So this is a reaction coordinate diagram looking at the nucleophile, which is the anion, in different solvents. So if it's in a protic solvent, recall that it would be stabilized very well by that hydrogen that's attached to the oxygen or nitrogen atom. And as a result of it being much more stabilized with a polar protic solvent, it will be lower in energy, and the activation energy will be higher for it to undergo that SN2 reaction. Recall that polar aprotic solvents do not stabilize the nucleophile well. And as a result, the nucleophile is higher in energy and will have a lower activation energy to overcome for the reaction to take place. So the bottom line is we use polar aprotic solvents in an SN2 reaction because it enhances the rate of the reaction. Okay, let's take a look at some other substrates. So up to now, we've only talked about alkyl halides. Alkyl halides are great substrates for substitution reactions, as well as elimination reactions, but we'll talk about that later on. But they're not the only substrate that can be used. We can also use what are called alkyl sulfonates. You can see here 3 different sulfonate-based groups. The difference is sort of in the R group attached to the sulfur. These are actually all great substrates for SN2 reactions. And because all of these are excellent leading groups, just like halide ions are. So you can think of bromide. Remember, we've talked about that as being a good leading group. And these are like, think of them as bromide alternatives. Okay, and so we often abbreviate these because it's quite time consuming to draw all of this out. So you'll often see this part abbreviated as the R group, O, and then either MS, TS, or TF, depending on if you're talking about the mesylate, tosylate, or triflate group. But when you see OMS, OTS, or OTF, what I want you to think is that's a great leading group, and this will be a great substrate for an SN2 reaction and some other reactions that we'll talk about in the future. So the reason why these are great leading groups are because once they leave, we'll have the oxygen. This should have a negative charge here. And it is highly resonance stabilized. So this anionic oxygen, right? The lone pair is stabilized up to the other 2 oxygens as well. So that large amount of great resonance stabilization means that that group can easily leave the alkyl group, the R group, because it forms something very stable. So which one is actually the best leading group? Well, it's important to note, and you should probably write this down in your notes, that the best leading group is the weakest base, right? So when you're talking about what's a good leading group, ask yourself, is this a weak base? If your answer is yes, then it's a great leading group. If your answer is, oh no, this is a strong base, then it's not a good leading group. So remember that base strength and acid strength are inversely related. So we can actually look at the pKa value of the corresponding conjugate acid to determine which would have been the best leading group. Recall that the one that's the strongest acid, which in this case is trifluoromethane sulfonic acid or triflic acid, will correspond to the weakest base, the strongest acid to weakest base, right? So this one is without the hydrogen, right? The conjugate base of this would be the best leading group because it's the weakest base. So how are these mesylates, tosylates, and triflates actually made? They're made starting from an alcohol. So what we'll learn is that an alcohol is actually a poor leading group. It is not a strong leading group because think about if I kicked off hydroxide, ask yourself, is hydroxide a strong or a weak base? Right? Most people know that hydroxide is a strong base. And I just told you that good leading groups are weak bases, right? So hydroxide is actually a poor leading group, but we actually can convert it into a good leading group if we convert it to a mesylate, tosylate, or triflate. So what we'll do is we'll take the alcohol, add in some mesyl, tosyl, or triflyl chloride, and it will do a substitution reaction to remove the chlorine. And then a base can come in and take the proton to give us a neutral product. And again, this is just often abbreviated as ROTS. So what I want you to recognize is that these are the reagents, right? MSCl, TSCl, or TFCl, and PY just stands for pyridine. So these are the reagents that convert an alcohol to, in this case, a tosylate. And what I want you to remember about this is that what I've done is taken this poor leaving group and converted it into a good leaving group. Now it's ready for an SN2 reaction. Recall that we need a good leaving group because the leaving group needs to leave in the rate determining step of an SN2 reaction. So poor leaving groups won't do. So in order to convert an alcohol to a good leaving group, this is one way to do it. And this is perfect for an SN2, getting ready for an SN2 reaction. Now, this good leaving group can be treated with any nucleophile, strong nucleophile, and it will do an SN2 reaction on this carbon and invert the carbon. So then the nucleophile would end up on a dash. Recall that you can see that the S configuration here has not changed. So converting the alcohol to the tosylate has not changed the configuration of a chiral center. The configuration of the chiral center only changes during the actual SN2 reaction with the strong nucleophile, where inversion will occur. Okay, so when you see substrates like this where it says OTS and OMS, I want you to think of that as sort of equivalent to a chloride, bromide, or iodide. They are all good leaving groups. And so they can be treated with a strong nucleophile to undergo an SN2 reaction. Recall though that the substrates do need to be unhindered, right? So methyl would be best. None of these are not methyl though. This is a primary substrate because this alpha carbon only has one carbon attached. This is actually a secondary substrate. Secondary substrates can go either way. Sometimes they react well in SN2 reactions and sometimes they don't. And it can depend on other factors, such as the reagent that's used. So this is a strong nucleophile, sodium azide. N3 minus or azide is a strong nucleophile. It is not also a strong base, and that's going to be critical for secondary substrates. And we'll learn about that when we talk about elimination. So given that the substrate only acts as a nucleophile and not a base, you can do SN2 reactions on secondary substrates. Recall that if it's a chiral center, oh, you know what? This is an error on my part. This should not be a chiral center because there's not 4 different groups attached. So I made a mistake on this one. And I'll fix it later. But let's pretend like this substrate does have a chiral center, right? It would be inverted. Remember that inversion occurs with SN2 reactions. If there's no chiral center, then you can go ahead and replace it with the nucleophile and you don't have to worry about inversion. So let's talk a little bit about synthetic strategies. I know I sort of jumped to the end of the chapter if everything is combined in one chapter, but it's important to start thinking about these synthetic strategies early, even if we've only learned about SN2 reactions up to this point. So organic synthesis is an entire branch of organic chemistry that's devoted to synthesizing more complex molecules from readily available and inexpensive starting materials. So we'll be looking at synthetic processes, which is basically the synthesis or making something from something else. And we'll start with just one-step transformations and move to multi-step transformations. But you've learned an important skill in this chapter. If you have an unhindered, like a primary alkyl halide, this is a great substrate for SN2 reactions. You can treat it with a variety of different nucleophiles, and this slide is really great for showing you different possibilities for different strong nucleophiles. and do an SN2 reaction to get a different product. Don't worry about this. This is going to be an elimination reaction, and we haven't talked about that yet. This we'll talk about a little bit later in the chapter as well. So if you don't understand some of the stuff in this section, don't worry, we will get to that. So some synthetic strategies. You actually now know how to do a two-step synthesis. And that, as we grow our knowledge of being able to do multi-step synthesis, we'll start with sort of 1 step and 2 step, and then we'll be able to actually move on to 3 steps and 4 steps, and you get the idea. Multi-step syntheses as we move through the year of organic chemistry. So what is it you know how to do? Well, remember that from the radical halogenation chapter, which is either chapter 10 or 11, depending on the edition of the book that you're using, we learned how to convert alkanes into alkyl halides. Recall that we can use bromine and either light or heat to do that radical halogenation reaction. So that's actually the first synthetic step that you learned. In this chapter now, you've learned how to convert alkyl halides using SN2 reactions into a variety of different substrates. For example, and if you use sodium hydroxide, you could make an alcohol product. And then you learn that a polar aprotic solvent is ideal for SN2 reactions. And there are lots of possibilities for what solvent that could be. So I sort of just generically wrote it in as any polar aprotic solvent. So when we're talking about synthetic strategies, there are multiple ways to analyze different problems when we're looking at how we can sequence reactions that we know in order to convert something to something else, regardless if it's 1 step or more than 1 step. And oftentimes we start with the desired end product, right? What are we wanting to make all the way at the end, right? And then we sort of work backwards to get to a reasonable, cheap, inexpensive, and readily available starting material. And of course, you might have to work backwards 1 reaction, or if you can't make that desired product in 1 reaction, you might have to work backwards with multi-reaction sequences in order to figure out a way to make the product. And the analogy here is that, like if you wanted to build a house, right? First, you would have blueprints, you would pick plans, you would imagine what the house would look like. Then you would decide what things you need to make that house, right? So organic synthesis is kind of the same way. We start with what is the desired product, and then think, how can we sequence, or how can we work backwards from that desired product to think about what we would need to get there? So this approach of working backwards from the product is called retrosynthetic analysis. And we can use retrosynthetic analysis, for example, to think about how we could synthesize this ether. So if we look at this ether and go, how can I make this, right? We want to think about what bond could I target to make, because I know a reaction that will make that bond, right? So for example, you might figure out that you can make this bond. So retrosynthetically, you would break this bond, right, into 2 pieces that you could use, or a substrate and a reagent that you could use to make that bond. So we know we can make this bond through an SN2 reaction. If we were wanting to make this bond through an SN2 reaction, we would typically start with an alkyl halide. This is great because it contains a great leaving group and a strong nucleophile, such as sodium ethoxide, right? So thinking backwards, we identify a bond we want to make, a reaction that can be used to make that bond, and then break it apart into substrate and reagents. We could also have envisioned making the other carbon-oxygen bond in the ether. If we did that, we would have come up with a smaller alkyl halide, in this case ethyl bromide, and a larger alkoxide ion as the reagent base, right? So this is the nucleophile, this is the electrophile in that direction. So there's actually more than one way where you could potentially make this product through an SN2 reaction. So you'll find that by thinking backwards, often more than one reaction will come to mind when trying to make a target compound. So the last step is to verify that the reaction you have proposed is reasonable, right? So if we're targeting an SN2 reaction, we know that we need an unhindered alkyl halide or something with a good leaving group. Primary alkyl halides work great in SN2 reactions. Also, we know we need a strong, ideally unhindered nucleophile. Unhindered because, of course, remember, steric hindrance can prevent or raise the rate of basically make the reaction slower, right? So an unhindered strong nucleophile is great for an SN2 reaction. And in the activity, we'll look at some differences between what will be considered unhindered versus more hindered. So that might not make too much sense to you, but hopefully as you work through the activity, you'll see some different examples and see why I'm calling this an unhindered nucleophile. It's a strong nucleophile because it has a negatively charged oxygen, and we know that makes a great nucleophile. So when you see NaO, recall that this is just sodium cations and an oxygen anion. That's a strong nucleophile. It is not very sterically hindered because this R group is small. Look at we can even throw in a polar aprotic solvent such as DMSO because we know that that's the ideal solvent for an SN2 reaction, and a primary alkyl halide, and this should be a fantastic SN2 reaction that will work quite well. All right, we'll stop there and you can continue with the activity.